The quadratic function is one where y will increase as x increases, but at a decreasing rate, right? We talked about this logarithmic function before. If we have here, we have two images. We have a linear approximation of the log, this is the logarithmic function, and then we have a quadratic approximation of the logarithmic function. Salary over somebody's career might look like this. So your salary might rise very quickly early in your career, and then it kind of levels off. And if you think about it, you know, like if you think about this as the y being percentage increase, that's definitely going to be the case, because you're going to move up and your salary is going to increase pretty rapidly, and then it's going to kind of level out where you may get increases, but as a portion of your salary, those increases are less and less large in terms of magnitude, right? They make up a smaller and smaller percentage of your salary, those increases. So a 10%, a $10,000 raise may be enormous. It may double your salary early in your career, but a $10,000 a year raise, if you're making $150,000, is going to be a pretty small difference. So that 150 to 160 is smaller magnitude than that 10 to 20 was. And so that's kind of what we're seeing in this curve. So we could see this in terms maybe also of improving physical health by tracking a change in BMI with a new diet or exercise plan. Initially, you would implement those new routines and your BMI would drop quickly. But then as you continue to do it, it can only go so low, you know, within the healthy range, it can only go so low. And so the impact of continuing that is going to be lower and lower as you go through. You can think of the same as weight. Somebody tries out takes a new diet, and they lose weight very quickly at first because they have a lot to lose. But the longer that they're on that diet, the less impact that diet is going to have on their weight. They do not lose at the same rate all the way through the process. So note the differences here in the linear and the quadratic model. We have a lot more variation. We're not fitting the model nearly as well as we are here. So we're still not fitting it perfectly, but we're getting a better approximation of the model using the quadratic function. And again, we're only seeing a portion of that parabolic model that I showed you here. We're catching just a piece of it. Maybe this section here, sort of tilted, is what we're seeing over here. But it still does a better job of approximating this logarithmic reality of the data with the limitations of our mathematical equations. How do we check for nonlinearity? Scatter plots can be somewhat useful. They can show us if there's something nonlinear happening with the data. But they may not be useful enough if you don't have enough data points to see a clear pattern, or if you have so many data points that it becomes difficult to distinguish a pattern. Last week, I showed you how to plot the residuals using SPSS to control for some of the other variables. Doing these partial residual plots can provide us with some clues to the relationship and to potentially nonlinear equations. In these cases, Allison suggests trying to fit polynomial functions to the data and assessing the models to see if they improve with different equations. And this may seem like a trial and error system, and in reality it is. If you find that a cubic function gives you a better r² value than the quadratic did or than the linear did, then that gives you a sense that you have a nonlinear function. So there's still some of that manual thought processing that goes into it. SPSS isn't going to tell you this is nonlinear and this is the formula that you should use. You should be using a cubic function or a quadratic function here. You're going to have to figure out through testing those different models which one gives you a better fit. Another way to deal with nonlinear relationships is the use of dummy variables. We can talk about the example of income over time. And we already talked about the interpretation of using dummy variables in terms of adjusted differences. And we also saw that dummy variables can be used for nominal variables that have more than 2 categories, where we create a reference group and then recode all of the other variables, leaving out that reference category for comparison. And then we run separate regressions on them. And remember that you always want to have 1 fewer dummy variables than the number of categories in your variable. And by running them separately, you get to see how things like marital status and so on, where we omit currently married. That was the example we used last week. And you compare to the one that's not included. And we can interpret our p-values as telling us whether there's a significant difference between the category that we measured and the reference category that we didn't measure. And that gives us a sense of whether those 2 different categories have different lines, right? They have different slopes. And so those regression coefficients are going to show up differently. Allison suggests that you use the category that has the highest number of cases if you are running them against a reference category. So because sample size is important, you want your biggest case to be your reference category. Otherwise, you can't trust the outcome of those regression models because you're comparing it to an inefficient model because it's based on such a small number of cases. And so using that the largest one will make your model more robust. In some cases, 1 or more of our independent variables may not be a continuous measure. And for example, it could be a nominal or ordinal. And so we can use these dummy variables as a way to deal with that. Dummy variables are widely used in regression analysis, and some regression programs allow you to do global tests of the coefficient that all the dummy variables are equal to 0. And there are statisticians who say that this is a really good idea if you have that ability within your regression program to do that. So when we use dummy variables to represent nonlinear relationships, it can help us to address the multicollinearity issue because we haven't put that other one in the model, right? If we included that reference category, then we'd have perfect collinearity. But leaving out that reference category, as we do when we run with dummy variables, we can address that multicollinearity issue because there's something missing from the model that protects us against that multicollinearity. We can, using dummy variables for representing nonlinearity and regressions gives us 2 benefits over using the polynomial models that we just talked about. First, it doesn't force a pattern onto the variables that may not be there, right? So it's trying to find, in the same way that using linear regression when it's nonlinear is forcing a line through it that isn't present in the data, if you are forcing a polynomial line, a curved line, you're doing the same thing. So it's easy, it also makes it easier to interpret because there are no exponents. So when we have polynomials, then we have squared terms and we have to figure out how to talk about it in terms of squared terms. Some of the disadvantages are that the division of variables can be arbitrary, particularly if we're talking about a multinomial variable or an interval ratio or ordinal variable. You're making a choice to break something into multiple categories. So if you take age, why choose 18 to 25, 26 to 35? Why is that age grouping important or better than some other arbitrary age grouping you could create of a sort of like under 35, right? And put all of those people together. The other disadvantage is that you get more coefficients. You get a coefficient for each group that you create, for each of those coded groups that you create, and that reduces the precision of your estimate. And again, this can be particularly problematic with small samples because the more coefficients you have, the more problematic your model in terms of reaching statistical significance. So dummy variables are best used when we have large samples. And we've talked about, we always want bigger samples than the biggest samples we can possibly get. And we're always limited in our sample size.